Hello everyone, thanks for joining. Today we will be talking about predictive engineering analytics with FloEFD. So let's look at the agenda. First we'll start with business impacts, challenges, then a new way forward, describe what FloEFD really is, do a first look demo, talk about customer success, and then finally summarize with removing barriers to innovation. So the first thing we will discuss is industry challenges and business impact. Any industry that looks toward the future is driven by innovation, striving to outperform their competitors. Companies are faced with increasing complexity across multiple dimensions, making products smarter by integrating mechanical with electronics and controls, ensuring quality while adopting new materials or manufacturing methods, taking advantage of opportunities afforded by the advancements in cloud and IoT. Therefore, product innovation is at an all-time high, and we are confronted by an explosion of complexity to cope with those expectations. Compounding the situation are the conventional pressures of time, scope, quality, and cost. However, in the face of increasing complexity, these pressures are even more challenging to navigate. So what does this mean to the business of engineering? To quote Lee Iacocca, an engineer and leader, organizations constantly face seemingly insurmountable problems, but these also represent great opportunities. So now let's move on to the next section, a new way forward. Extending that thought to your organization, you and your teams are faced with many challenges, engineering trade-offs that may seem impossible to solve, making your product more powerful yet consume less energy, making your product faster yet reducing the noise level, making it thinner yet cooler, making it more complex yet get it to market faster. So how will you navigate these trade-offs and answer the tough questions to bring innovations to market faster, despite the increased complexity? Answering these questions requires solutions that can help predict and improve performance. This is what brings the digital twin to life. Hence, we consider simulation and test the beating heart of the digital twin. Simcenter is a flexible, open, and scalable portfolio of the best predictive tools on the market. Simcenter FloEFD is a part of this outstanding portfolio, which covers the full breadth of engineering methodologies. So, what exactly is FloEFD? Simcenter FloEFD is a front-loading, multi-CAD embedded CFD tool for designers. Front-loading is the concept of performing your simulations earlier in the design cycle to maximize the impact and catch issues before the late-stage validation phase. It is fully embedded in the PLM design environment and has unique automation technologies. FloEFD is a general-purpose tool which can be used in a wide range of flow and heat transfer problems. It has been specifically developed for non-CFD specialists to use to get fast, accurate results. The Mesher and Solver have unique proprietary technologies which facilitate the streamlined CAD-embedded analysis approach of this product. The result is a drastic reduction in barrier to entry and overall CFD simulation time. We have seamless integration with Dassault CATIA V5, PTC Creo, NX, and Dassault SolidWorks. We also have links to the Inventor and Solid Edge environments. We'll be looking at the NX version in this demo, but the process is identical for other MCAD systems. The benefits of this is that there is no translation from the CAD model. Any CAD design changes are instantly reflected in the CFD analysis. Synchronization of CAD and CFD becomes a non-issue. So now let's dive into predictive engineering analytics with FloEFD. We will walk you through 6 steps in the simulation process over the next 15 to 20 minutes. We will use FloEFD to analyze an IGBT liquid-cooled module, which can typically be found in an electric vehicle or renewable energy applications. These modules are used when large amounts of current need to be switched on and off rapidly to control a motor, for example. The power semiconductors can generate kilowatts of heat under sustained load, so liquid cooling is the only way to keep them operational and reliable. A typical results visualization can be seen here, with the temperature variation on a surface plotted along with the water flow streamlines. The process will be geometry manipulation with the NX integration, analysis setup, meshing, solve, review the results of the analysis, and then optimize the original design and quickly create a new best simulation. So now let's see how FloEFD can improve your innovation process. The first step to be covered is the NX integration. FloEFD is natively embedded in Siemens NX. We support the latest versions of NX all the way back to NX7. This means there is no need to transfer geometry from CAD to a CFD tool. All of the assembly and part parametric definitions are maintained, so modifications can be made easily. This is especially powerful when it comes to optimizing the geometry. Compare this with using neutral file formats like STEP, where all parameters are stripped out and you're left with a dumb solid. The fluid region is automatically detected based on an internal flow region, and this is updated with geometrical changes also. The image shows the water region detected by FloEFD. Let's look at some of those features in FloEFD. So now let's go on to the live demonstration.
Here is the NX interface in modeling mode currently. If we explode the assembly, we can see the parts which make up the IGBT cooler. It's important to model all the materials in the thermal path from the semiconductor to the fluid. We can see the silicon, the solder, the copper chip carrier, and the thermal paste attaching the chip carrier to the base plate. The casing is made of aluminum, and the whole assembly is designed to operate in vehicle underhood conditions. There is the addition of lids, which serve the purpose of closing the water region and for applying flow boundary conditions. Let's look at the copper base plate in more detail. If we open the part, we can see it's been designed very simply in NX using an educated guess for its predicted performance. Looking at the NX expressions, we can see there are 3 parameters controlling the heatsink pin width, draft, and pattern spacing. The model has been designed this way with later optimization in mind. Jumping back to the main assembly and taking a cross-section, we can see there is some geometrical overlaps between the parts around the O-ring and silicone potting compound. FloEFD has no issue with overlapping and dirty geometry. There is no need to spend time fixing this, just be careful with material priorities. FloEFD is started from the menu tree under Simulation. This starts FloEFD mode and checks out the license. We can see the addition of the Flow Analysis ribbon toolbar, which is used to control the analysis. The lids on the inlet and outlet can be created automatically using the Create Lids tool. Finally, let's use the FloEFD Check Geometry functionality to check the fluid region. Clicking on the Show Fluid Volume button will highlight on the screen where the fluid regions are. There are some small enclosed volumes around the O-ring which can be ignored later, but the main flow region has been detected correctly. This fluid volume part doesn't need to be created in NX. It is automatically created and updated. The geometry is now ready for FloEFD analysis.
So the benefits of having an NX embedded approach are that there is none or minimal geometry simplification necessary. Geometry changes are detected and the project is updated automatically. The tool is easy to use for existing NX users as it's just an extension of the CAD tool. So what we just saw was the NX embedded nature of the software and how designers can leverage pre-existing NX models to perform a CFD analysis. The familiarity of the NX interface and FloEFD being a logical extension makes the tool easy to use for the NX designer. So now that we have prepared and checked the geometry, we're ready to set up an analysis on the assembly. The FloEFD project is created using a wizard-driven process. Flow and thermal boundary conditions are applied directly onto the NX parts. If materials have been applied in NX, these can be imported directly into the FloEFD engineering database. So now let's go on to the live demonstration.
Let's start the wizard and look at the steps. The first step is to name the project. We can also see that the project can be created on the NX family of assembly members if needed. This project is an internal analysis, as the inlets and outlets are well defined. The exclude cavities without flow conditions is enabled to ignore the previously seen cavities. Heat conduction in solids is enabled to consider conduction and convection. Water is chosen as the working fluid. The wall conditions are left at adiabatic to ensure all heat is transferred to the water. The ambient temperature is set to 65 C to replicate under-hood conditions. Once the wizard is finished, we can see the computational domain around the assembly, which has been sized automatically based on the wizard selections. Let's quickly import all the NX materials which have been assigned. The assembly is scanned and we can accept the detections. Materials can also be applied manually. Here we're applying silicon on the chips themselves from the independent FloEFD materials library. This is useful as not all NX material definitions have temperature-dependent properties. Next, we'd like to assign the water flow conditions using a boundary condition from the ribbon. A volume flow rate of 1.5 gallons per minute is applied to the inner face of the lid we created earlier. The thermodynamic properties show the inlet water temperature of 65 C. In a similar manner, an outlet pressure condition is applied to the other lid. This will allow the water to leave the system and gives a known pressure condition. A volume source is used to apply a heat load. Multiple parts can be selected at once and the power will be split across the bodies. We'll apply 360 watts on the IGBTs and 144 watts on the protection diodes. Like this, other FloEFD features can be applied directly onto the NX geometry.
The FloEFD project is initialized with a wizard and can be applied at any stage of the design process. The engineering database can be shared across a team to ensure consistency. FloEFD data can be reused and persistently associated with a part if desired. Projects can be cloned and templates created to standardize the analysis setup stage. So, to recap what we just saw, the analysis setup is performed in NX using a wizard-driven process. Analysis boundary conditions are applied onto the assembly parts and features. The benefit of this step is that it's quick and intuitive to set up an analysis for the design engineer. So, traditionally, one of the trickiest and most time-consuming aspects of CFD has been the geometry meshing stage. The fluid and solid regions are discretized into grid cells, which is then passed on to the solver for solution. It's normally at this stage that requires the geometry to be simplified for meshing, or simulation compromises have to be made for the sake of solution time. FloEFD uses proprietary smart cell technology to alleviate a lot of the issues associated with the old way of doing things. Smart cells can have multiple fluid and solid control volumes to simplify the mesh generation step. Complex CAD models are meshed with minimal user input using an automatic mesher. Solution adaptive mesh refinement can even increase grid density mid-solve based on local flow gradients. So now let's go on to the live demonstration.
If we go normal to the screen in NX, we can show the global mesh settings for FloEFD. At present, the automatic mesh is applied at level 4. We can move the slider to increase or decrease the global mesh density. FloEFD uses a finite volume method on a Cartesian grid to solve the Navier-Stokes equations. The mesh on the screen is only the base mesh before any cell subdivision has occurred, and is visualized to give the user a rough idea of how fine the final generated mesh will be. The mesher can be switched over to manual settings if desired, where cell sizes and refinement settings can be accessed. User-defined local initial meshes can be employed to manually apply finer grid on specific parts and areas in the model. The mesh has already been generated for this model, so now let's have a look. If we zoom in around the base plate pins, we can see a finer mesh around the heatsink where the flow is constricted. The current plot is colored by levels, which can range from 0 to 9. Octree refinement is employed to split a single base mesh cell into 8 smaller cells to increase to the next mesh level. This can happen up to a maximum of 9 times to create exponentially smaller cells. This Octree method performs 2 important tasks. First, the aspect ratio of every cell is identical. The smallest cell has the same aspect ratio as the base mesh. The second is that the growth ratio is restricted to a single level to avoid very small cells transitioning into large cells. These are both important for solver robustness and convergence behavior. The smart cells are always found at the interface between fluid and solid. This is where the boundary layer forms and the convective heat transfer occurs. Smart cells can have multiple control volumes, up to 12 in a single cell. It's this technology which makes FloEFD meshes easy to generate and tolerant of dirty CAD geometry. If we plot the surface of the heatsink base with mesh, we can see the smart cells which touch the water region. Proprietary wall functions are used in the smart cells to apply the boundary layer. FloEFD uses the K-epsilon model for the bulk flow turbulence and an empirical engineering model for the near wall effects, which have been calibrated over a wide range of Reynolds numbers. Now let's have a look at the solid conductivity in a 2D plot through the model. A smart cell can have multiple solids within a single cell, up to 36. This makes resolving thin solids, such as thermal interface materials, very straightforward and easy. When overlapping parts exist, such as between the sealing O-ring and the base plate, there is a material hierarchy which can be edited to get the correct material dominance.
The benefits of FloEFD's unique mesher are that it's very simple for a non-expert to generate an accurate grid. The boundary layer is handled automatically without the high cell count requirement at the wall. The mesher has a default automatic setting which can be augmented with manual conditions if desired. So to summarize, we saw how FloEFD discretizes the domain into finite volume grid cells using an immersed boundary approach. The FloEFD smart cells remove a lot of the complexity of meshing, which has traditionally been a stumbling block to reliable CFD results. FloEFD removes these barriers and allows non-experts to generate a robust mesh. So now let's have a look at some of the features of the FloEFD solver next. FloEFD uses its own proprietary solver similar to its own mesher. It exhibits very robust convergence behavior due to some of the features covered in the meshing section. The classic 3D CFD solving approach is employed, which is augmented with engineering models to provide empirical correlations. This is especially pronounced in the boundary layer treatment. Wall functions are used in conjunction with the smart cells at the boundary layer, which means a coarse grid can be used at the wall without any consideration for for Y+ tolerances. All of this technology is implemented without requiring any user input, again to reduce simulation complexity and promote ease of use. User-defined engineering goals can be specified to extract key performance data and are also utilized to monitor solution convergence. So again, let's go on to the live demonstration.
Moving further left in the ribbon toolbar, we can see there are several goal types we can apply to the model. Goals can be in the form of global, point, surface, volume, and equation depending on what needs to be measured. In our model, we've got goals for inlet water pressure and outlet water temperature. This will give us our delta P and delta T. Volume goals are used to monitor the maximum temperature on the IGBT and diode parts, as these will be the hottest components in the model. The equation goals are at the bottom and are manually created to easily digest the deltas between the goals. During the actual solver execution, the usual Navier-Stokes equations are being solved to ensure conservation of mass, momentum and energy, but the solver is also checking the goals to ensure steady-state convergence behavior before the solver will stop. The convergence criteria can be adjusted for user-defined accuracy. If we look at the solver options, we can see that the mesher needs to be run before the actual solver. The mesher and solver are both parallel compute enabled and can utilize as many CPU cores as needed. This is by default and requires no additional license. The FloEFD license is also network floating by default, which means the CPU-intensive solving process can be offloaded to a dedicated solving machine or server. The option to close the CAD is available, so the NX license can be freed up if the solve will be long. While the solver is running, the goals can be monitored graphically to ensure sensible results, and preview plots can be created to ensure results confidence. This particular model takes about 5 minutes to generate a mesh for and about 20 minutes to solve the convergence.
The benefit to the user of the FloEFD solver is that there is automatic monitoring and convergence behavior using intuitive goals. The solution can be monitored in real time to ensure results are sensible, and there haven't been any errors setting the model up. The solver can be run on a remote machine to free up local resources. To summarize what we saw, the solver has many unique features which ensure reliable results. The solver exhibits robust convergence behavior driven by user-defined goals. The process is seamless and the user can expect quick, accurate results with minimal manual intervention. So everything we've seen up to this point has been done so that we can produce the results necessary to predict the product performance. Similar to the FloEFD pre-processing, the post-processing is performed within NX also for an intuitive user experience. Flow and thermal results can be visualized directly on the NX assembly, and we can create various plot types. Numerical performance data can also be extracted in Excel and Word format for maximum flexibility. So now, let's go on to the demonstration.
Cut plots can be used to take 2D slices through the model along predefined planes. The cut plot is currently showing temperature, and the legend can be adjusted to understand the range of values. We can probe the plot to get mouse cursor values of the temperature. The plot can be animated to move the slice through the model. It's easy to change the parameter to velocity, and we can see the flow winding through between the pins. We can also visualize the pressure variation, which gives us an idea of the pressure drop across the unit at this prescribed flow rate. Surface plots can be used to look at temperature variations. We can see the chip carrier temperature with the hottest region on the silicon dies. If we color the heatsink, we can see the cooler region in contact with the water. Flow trajectories can be used to see how the flow moves through the fluid region. The flow can be animated and exported if desired. Animating the flow is useful for detecting recirculation zones or area of high flow velocity. The goals which are used for convergence can be plotted on the screen showing the final steady-state values. We can also see on the graph the convergence behavior of the goals with iterations on the x-axis. The goals are smooth and plateaued, indicating a converged solution. The data can be exported to Excel for further data analysis. NX sketches can be created and used for results extraction, even after the solver has been run. Here we have a line along the bottom of the flow region, and we can plot the pressure and temperature change along the path. Again, the data can be exported to Excel for further processing. A new feature is the flux plot, which is a novel way of visualizing heat fluxes between NX parts and assemblies. If we create a flux plot on the heatsink, we can see how much and where the heat is flowing into and out of the heatsink. The power filter is used to show where the power is coming from and how it eventually all goes into the fluid subdomain. A report can be created based on templates, which can be customized to export only selected data if required. FloEFD results can be exported to FEA, including Simcenter 3D and FEMAP for fluid structure interaction co-simulation. There is also a free, unlicensed FloEFD results viewer called FloEFD View, which can be used to look at results completely divorced from the NX UI.
As we've seen in looking at the results, FloEFD allows you to visualize performance in a way the physical test cannot. You can really interrogate the results and get to the root cause of a flow or thermal issue. The data can be exported easily to Excel and Word in a standardized format for comparative use. A free unlicensed viewer is included on the installer image for sharing results with customers or internally. To summarize, FloEFD makes looking at the results very easy for the user, as it's simply an extension of NX. The data can be seen visually with plots and streamlines or be exported to Word and Excel for quantitative analysis. Either way, the key performance data can be easily evaluated and used comparatively to guide engineering design decisions. So now let's look at the sixth and final step in our demo, which is design exploration. Design exploration is the process of augmenting the base case simulation to look at variance and ideally optimize your design. As FloEFD is NX embedded, we can leverage NX expressions directly as input variables. Alternatively, the project can be cloned onto a predefined family of assembly variants. There are several parametric study options available for looking at scenarios based on simulation or geometric inputs. So now on to the live demonstration.
Let's start the parametric study from the ribbon toolbar. As we can see, there are various options available depending on what needs to be achieved. The design of experiments and optimization is a FloEFD native optimizer which uses a brute force approach to seek an optimum. A new optional module is the HEEDS optimizer, which has a more intelligent algorithm. The first tab is the Input Variables. We can select simulation inputs, NX expressions, assembly constraints, or part family parameters. Let's choose the NX expressions. We saw right at the start how the base plate was designed with expressions controlling some of the features. Here is where we can select the three parameters of interest: the diameter, draft angle, and pitch of the heatsink pins. We then need to give a min-max range for each of these inputs. In the output variables, we can select the goal we'd like to optimize on. For this, I'm selecting the maximum IGB temperature, which we'd like to minimize, and the delta P, which we'd also like to minimize. We can also define some constraints here if there are any engineering guidelines for operation. For example, the cooler cannot have more than a 0.17 psi pressure drop. Finally, the scenario table allows us to select the optimization algorithm. As the delta P and maximum temperature are opposing goals requiring a compromise, we use the Pareto front to find an acceptable operating point. The software will then run 40 scenarios to calibrate the input variable sensitivities. Upon completion of the 40 runs, we can see the study plot showing a graph of the two input variables. The software has identified some feasible points and also an optimum scenario, in our case, number 37. We can right-click and create this project in FloEFD as the optimum. Jumping over to this design, we can see the denser pin arrangement but steeper draft angle for freer flow. This optimized variant has been saved automatically. Performing the parametric study allows the user to quantify the difference a design change has, and this has tangible benefits on product operation.
What we just saw was the use of the optional embedded HEEDS optimizer, which has market-leading intelligent optimization algorithms built in. The user can select input variables and the software will determine the best combination of them. The optimum can be saved as a new NX assembly member. To summarize, FloEFD allows users to perform simulation variants intelligently to quickly identify the best operating point. Not leaving the CAD means that the geometrical inputs are available for variation rather than an exported step file which has no feature tree. So now let's look at a customer success story. Mitsubishi needed a methodology to simulate the cooling and mechanical effects of a new nozzle, specifically liquid-cooled nozzles for cutting tools. They needed answers to the following questions. Would it produce enough cooling? Would the nozzle component be durable enough? As such, engineers and designers assembled an array of computer-aided engineering tools to virtually test the new design. For fluid flow and heat transfer analysis, they decided to use Simcenter FloEFD software. By utilizing FloEFD, the customer was able to obtain the following: improved 11% more cooling liquid flow rate and 57% higher peak velocities. Finally, let's move on to removing barriers to innovation. In conclusion, bottom line, FloEFD is easy, fast, and accurate. The features shown today highlight what makes FloEFD an easy-to-use, designer-level analysis tool for front-loading CFD analysis. Some of our core market segments can be seen here, such as auto, aero, plant, and process and power generation. It is a general-purpose tool which can be used anywhere your product has fluid flow or heat transfer phenomena. So thank you very much for your time and attention today. It is appreciated.